The Biomechanics 1 video series. We're looking at uniformly accelerated motion equations in this particular video. This one is going to also be subdivided into several sub-videos, starting off with the three equations that tend to describe uniformly accelerated motion. So there's a couple of factors that apply to this. In other words, for this to be true, acceleration has to be constant, and it therefore only applies to a limited number of situations. In essence, any straight line motion whereby the acceleration is unchanging, or any vertical motion whereby the acceleration tends to be unchanging. It can be under special conditions be also applied to projectile motion or curvilinear motion, which is one of the reasons why we have to look at this in a little bit more detail. This first specific video is going to be a little maths orientated. We're just going to kind of see where these equations tend to come from. It's a lot less complicated than it looks, but it does require a little bit of insight into some algebra at least. So without further ado, let's kind of just see where they come from. I'll start from the first equation and work my way down. Okay, so we all know by this stage already that acceleration is defined as the change in velocity over the change in time, whereby this change in velocity is defined as the final velocity minus the initial velocity. So I'll kind of just substitute that in there, and I'll just rewrite the same equation as being that the acceleration is equal to the final velocity minus the initial velocity over some change in time. And if I multiply this change in time out to both sides, I get that acceleration times the change in time is equal to the final velocity minus the initial velocity. And then all I'll do is I'll move this initial velocity over to that side, and I'll get this equation, which kind of looks like this: acceleration times the change in time plus the initial velocity is equal to the final velocity. So if I rewrite this to kind of look like that first equation, it's just a matter of shifting things around. Final velocity is equal to initial velocity plus the acceleration times change in time. There we go. First one, straightforward. That's the first equation of uniformly accelerated motion, right? So in this case, remember that acceleration is thought of as being constant. Okay, so we'll label this one as equation number 1. Excellent. Okay, let's go to equation number 2. So there's two ways to define average velocity. Remember, average velocity is defined as v with a bar on top. So average velocity is defined as the change in distance, whereby we'll just denote distance with an s, divided by the change in time, but also the fact that average velocity can be defined as the final velocity plus the initial velocity between 2 points divided by 2. Right, that's another way of looking at an average. So since average velocity is equal to this change in distance over time, average velocity can also be defined as this final velocity plus initial velocity over 2. I can make these two equal to each other. So I can say that this change in distance over change in time is equal to this final velocity plus initial velocity over 2. Okay, then what I'll do is I'll multiply both sides by 2, so I'll get this 2 times change in displacement over change in time is equal to final velocity plus initial velocity, and then I'll get final velocity on its own, so I'll subtract the initial velocity from both sides, so I'll have this 2 delta s over delta t minus the initial velocity is equal to the final velocity. Okay, so we're in a pretty good place so far. Now I can put these two equations together. So I've already got an equation for final velocity over here, and I've got an equation for final velocity over here. So I'm just going to use a new color to denote these two different components. So I can put these two equal to each other, so I'll use this one first. So I'll have the initial velocity plus acceleration times some change in time being equal to this side of the equation. So 2 times delta S over delta T minus the initial velocity. Okie doke, so what I'll do then is I'll get this initial velocity over to that side. So since I have an initial velocity which then becomes a plus, I'll have two initial velocities plus a times delta t, which is equal to 2 times delta S over delta t. So then I'll multiply all of these by this delta t so I can get rid of this. So then this becomes 2 times vi times delta t plus, and this is going to become a times delta t squared is equal to 2 times delta s. And then what I'll do to get rid of these 2's is I'll divide everything by 2. Pretty straightforward. So if I divide this by 2, it just gives me vi times delta t plus, if I divide this by 2, becomes 1/2 a delta t squared is equal to, and if I divide this by 2, it just becomes delta s. So again, I'll just rewrite this slightly. So in essence, it's saying delta s is equal to vi delta t plus 1/2 a delta t squared. And there we go, second equation done. That's equation number 2. This is quite a useful equation. I'll add a little step that you might see in some books. Let me take that the other way. Remember that delta S is just simply the final position minus the initial position. So I could rewrite this equation over here in a slightly different format, where I'll have this final position minus initial position is equal to vi delta t plus 1/2 a delta t squared. And I'll just bring this initial position over to this side so that I have the final position on its own. Let's undo that, which is equal to initial position plus vi delta t plus 1/2 a delta t squared. The reason that this is a slightly more useful component is, in essence, you're describing the position of an object at any point in time, right? So this component over here, let me just choose a different color quickly to make it a little bit more clear. This component over here says what is your how much further you would go when there's no acceleration. So when acceleration is equal to 0. So you might think, well, how the heck does velocity times time equal to some change in position? Well, if you remember that velocity is equal to some change in position over some change in time, right? So if I multiply both of this out, it says that v times change in time is equal to change in position, right? So this over here gives me some insight, saying that your change in position is equal to velocity times time, or when you move from one position to another, you can calculate based on how fast you were moving and for what time you were moving, how much your position tended to change. Okay, so that's where this kind of area comes from. This component over here tells you, let's just put the explanation here, how much further you travel when there is acceleration, or when acceleration is not equal to 0. So in other words, there is acceleration. And you might think, well, how the heck is acceleration times time squared linked to the position of an object, right? Well, let's go with this component. We also know that the acceleration is some change in velocity over change in time. So change in velocity is equal to a times delta t is equal to change in velocity. Well, velocity is also a change in position over change in time. So if I chuck that in here, that means, and sorry for writing all over the place, but I'm just trying to make sense of some of this stuff, is this change in position over change in time. So if I multiply time out by both sides, I have this kind of change in position is equal to at squared. Okay, mathematically it gets derived from all this other stuff, but it just gives you a brief overview that there is some kind of link between change in position and this concept of at squared, right? So whenever there is acceleration, it describes the position as a function of how much acceleration there is and how long that acceleration tends to be acting for. Okay, so in any case, that's our second equation. Very, very useful, specifically when it comes to projectile motion later on. But it leaves us with one more equation to derive, which is probably the most algebraic one out of all three. So if you didn't think it can get worse, yes it can. So I'm going to try and take it slowly, so just try and bear with me. Okay, let's see where my pointer is. Okay, so the next one says that acceleration, which we've already derived, is equal to the final velocity minus the initial velocity over time, right? This delta t. Okay, so if I rewrite this in the form of delta t, I can bring that up there. Again, we already derived this component, but we're just going to make the delta t the subject of the formula. The final velocity minus the initial velocity, and then I'll divide both sides by a to give me delta t on its own, which says that it's the final velocity minus the initial velocity over acceleration. Okay, so now I have an equation that gives me the time as a function of velocity and acceleration. I will plug this into these time variables over here. So I'm just going to plug it in there, and I have a delta t over here. So when I substitute this delta t for this, I'm going to get a really messy looking equation. And I'm just going to simplify this final position minus initial position as a delta s. So it's going to give me this delta s is equal to this initial velocity, right, times time, or times delta t, but delta t is equal to all of this. So I'm just going to write that in there. So it's this final velocity minus initial velocity over acceleration plus 1/2 a and delta t squared, but remember delta t is now all of this. So it's Vf minus Vi over a, and it's all of that squared. Alright, so I will need to multiply this out. So this Vi multiplied by all of this, and I'm going to have to square this. So just to make this a little clearer so it doesn't get too messy, Vf minus Vi over a squared is going to be, I'll just rewrite it up here. So Vf minus Vi over a and all of that squared is going to look like this. Vf squared minus 2Vf times Vi plus Vi squared over a squared. Okay, so this becomes this, which I'll replace in here. Okay. Nope, other way. So then all of this becomes delta S is equal to, and now I'm going to multiply this out, VI times VF minus, and a VI times VI is a VI squared, and it's all over A, plus 1/2 A, and then all of this became all of that. So let me just write that out. VF squared minus 2VF VI plus VI squared, all of that over A squared. Nice. Looks horrible, right? Okay, let's try and clean this up a little bit. So an A divided by an A squared, so one of these disappears. Oops. One of these disappears and this A disappears. So let me just write this, rewrite it. All of this becomes this now, that this delta S is equal to VI times VF minus VI squared over A plus 1/2, and now, like I said, that A disappears. VF squared minus 2VF VI plus VI squared, and all of that over just A, because the A squared cancelled with the other A on the outside. Alright, we're getting closer. Let's see what else I can do. I'll multiply everything by A, so that I'll get rid of these A's at the bottom. So now this will become A times delta S, and that cancels now with these A's, is equal to VI times VF minus VI squared plus 1/2 all of this junk in here, VF squared minus 2VF VI plus VI squared. And remember, we've got rid of the A now because we multiplied it over to the other side. So it's starting to get better. What else can I do? I need to get rid of this half. So what we'll do is multiply everything by 2, because a half times 2 is going to cancel out. So I'll just have to do that on all sides. So this becomes 2A delta S is equal to, well, I have to halve or multiply that by 2, so it becomes 2VI times VF minus 2VI squared plus, and now I can just write this because that's been cancelled, VF squared minus 2VF VI plus VI squared. Okay, getting closer. We can cancel a couple of things. So you can see here is a plus 2VI VF minus 2VF VI. So this is going to cancel with this. I have a minus 2VI squared plus a 2VI squared. So minus 2 plus 1 gives me minus 1. So I'm just going to rewrite this one more time. 2A delta S is equal to minus VI squared plus VF squared. So I want to get VF on its own. I can just add VI to both sides. So this is going to become 2A delta S plus VI squared is equal to VF squared. So I'm going to write it in its final form, the one that you'll see in your textbooks all the time, which is VF squared is equal to VI squared, or initial velocity squared, plus 2A delta S. Wow, that was a lot of work just to get these three equations, but this is your third one. Okay, so if I take you all the way to the top, notice that we have derived all three equations. What is really important about all of these is that they each have something that one of the other three or other two doesn't have, right? So if you notice, let's just try and create some space here. Let's just see what I can do. Okay. I'll try and delete some of this stuff. Delete you. Delete you. And let's see if I can delete some of this stuff here. Yep. Okay, looks good. So that's giving me some space. Okay, so we have a couple of quantities. We have VF, we have VI, we have A, we have delta S, we have delta T. So what else? I think that's pretty much it. Okay, so you'll see this first equation will have it accounts for VF, absolutely. It accounts for VI, it accounts for A, and it accounts for T, but it doesn't have a delta S. Okay, second equation. It has a VI, it has an A, it has a delta S, and it has a delta T, but it has no VF. And if you look at the third one, again, it has a VF in it, it has a VI in it, it has an A in it, and it has delta S in it, but it doesn't have a delta T. Okay, so each one of the equations has something in it that the other one doesn't have. So how do you know which equation to ultimately use when you're solving various problems? Well, you look at the requirements, right, of the question. So I would suggest that you kind of, if you really stuck, try and create this kind of a table and look at what the question is asking for. In other words, it must have the variable of interest that you're trying to solve for, but it must also contain variables that you can plug in, right? So at the end of the day, it's a matter of finding the equation that has one unknown and three known variables. Okay, so it can only contain one unknown at the end of the day, really, so that you can solve for that unknown variable. I won't ever ask you to really combine two equations. I won't ask you guys to derive these equations. I've merely tried to show you where they come from. And in essence, they're all really boiled down to this simplistic understanding of the definition of velocity being some change in distance over some change in time, as well as the definition of acceleration, which is some change in velocity over some change in time. They all really boil down to these two fundamental equations, which are ones that you're already super familiar with, right? It just takes a little bit of clever algebra to try and rearrange these to get these uniformly accelerated motion equations. Okay, again, remember that it's purely based on constant acceleration. As soon as the acceleration tends to vary with time, we cannot use them. Okay, but again, it'll have lots of application, and we'll look at the projectile motion where we can use this quite well to predict what tends to happen to a projectile when it's in the air. Alright, I'll leave it there, and we'll cover the other videos after this.